Welcome to lecture number 11. Today we will talk about AC circuits, and that means that all the voltages and all the currents within a circuit are sinusoidal. Okay, let's start. Let's say we have a circuit and there is an AC current source, and this ideal current source delivers a current with an amplitude and the current is sinusoidal. And I made a computer simulation, and for our circuit I used these parameters. So the amplitude of our current is 1 ampere, the frequency is 50 Hertz, so the angular frequency is 2 pi times 50 Hertz. The resistor has a resistance of 1 ohm, the inductor an inductance of 32 millihenry, and the capacitor has a capacity of 1.5 millifarad. Okay, so our current is sinusoidal. I'll draw it here. Okay, and then I want to calculate and draw the voltage drops at our passive elements here. And you know that at a resistor we just have Ohm's law, so the voltage drop here is R times the expression for the current. And if I draw it, it's a sinusoidal voltage. The amplitude will be 1 volt because the current has an amplitude 1 volt and the resistor has the value 1 ohm. Okay, at the inductor we have a voltage drop too, and you know from lecture 7 that the voltage drop here has this amplitude and a phase shift of 90 degrees. And if we draw this voltage in our diagram, it looks like this. And at the capacitor, it's the same. We have a phase shift there, but now the phase shift is 90 degrees into the other direction. So the voltage drop at the capacitor looks like this. Okay, and now we could calculate the total voltage drop at our passive elements. And if we do so, we just use Kirchhoff's voltage law and it looks like this. Okay, and now the next graph is drawn by the computer. There it's easy, I just told him here you have this 3 voltage function and now add them. And it looks like this. But if you try to do that on your own with a pen and a piece of paper, you get crazy. Have a look into a mathematical book how to add sine functions with phase shifts and different amplitudes. You don't want to do that. So, but if we lean back and have a look at our functions, we can see that all the currents and all the voltages are sinusoidal. And they all have the same frequency. And the values differ only in their amplitude and their phase shift. So now it would be much more convenient if we could just describe our voltages and currents with a number value, and this number value should include the amplitude or the absolute value, and they should include a phase shift. What could we do? We have a solution for that, and those are the complex numbers. And if we use them, then they include an absolute value and a phase shift, and there are rules for addition and subtraction, and we can use that, for example, for Kirchhoff's current law and Kirchhoff's voltage law. And there's also the multiplication and division defined for complex numbers, and we can use that for Ohm's law, for example. So, believe me, usage of complex numbers is quite cool, because then our problems become easy. You can just calculate an AC circuit with complex numbers, and then it's as easy as dealing with DC circuits. Okay, let's just repeat what complex numbers are. I've drawn here a complex plane. So we have a real axis and an imaginary axis. And now we can describe a point in this plane as a complex number. And let's say we have this point where the arrow ends. There is the point of the complex number we want to describe. And now I could either describe this complex number with its coordinates. So I could say I have this real part of my complex number and my imaginary part, and therefore the complex number is real part plus j imaginary part. Now you might say, hey, why j? I learned that it's I. Yes, you're right, but in electrical engineering we use a j because we already use an I for currents. So this is just another definition for this imaginary number. Okay, but there's another way to describe a complex number. I could also describe it by their absolute value, and the absolute value is the distance from the center point of my complex plane and the point where the complex number is. And so a complex number has an absolute value and a phase angle. And then there is the so-called Euler's identity. And this means when we are in our complex plane and we have a number with the absolute value of 1, then all the numbers who have the absolute value of 1 will be on this circle here. And therefore, when I have such a number with this phase angle, we can describe this complex number with Euler's identity, and this is e in the power of j phi. It's quite cool. So this expression e in the power of j phi is a complex number. Its absolute value is always 1 and the phase angle is this phi. Okay, and with Euler's identity I can express our complex number here with its absolute value times e in the power of j and then this phi a. Okay, and we need mathematical operations. So the addition of complex numbers. Let's say we have a complex number a and a complex number b. And the addition is very easy. It's just like vectors. So you can just add them like vectors, and you see this here is the sum of the two complex numbers. And if you want to calculate it, it's just the sum of the real parts plus j and the sum of the imaginary parts. And the subtraction is obviously as easy as the addition. There you have to subtract the real parts from each other and the imaginary parts from each other. Okay, the multiplication of two complex numbers is done like this. Again, let's say we have these two complex numbers and we can express them by their absolute values and their phase shifts. And then the product looks like this. And the multiplication rule is that we multiply the absolute values and we add the phase angles. So the product looks like this. And for the division, it's the same thing. There we divide the absolute values by each other and we have to subtract the phase angles from each other. Let's go back to our example. So I said that we can express our current like this as a time function, but now we could express this current by a complex number. What we ignore is the frequency. We have to have the frequency in mind separately, and the frequency or the angular frequency is the same in the whole circuit. Therefore, we can just say we have an AC circuit and omega is this and this, and then we just know it and use it for all the values. Okay, and then we have here sinusoidal values, and you remember that we introduced the RMS value. The RMS value was this convenient number for periodic signals, which says that a DC voltage or current of the same number value would produce the same electric power in a resistor. And therefore, in our AC circuits, we will deal with RMS values. And therefore, for our current, we use the absolute value. It's the amplitude divided by a square root of 2, because that was the RMS value of a sinusoidal function. And let's say that our sine wave is our orientation, and therefore our current has the phase angle 0 degrees. Okay, and now let's have a look at the voltages. The voltage at the resistor just looks like this. And if I want to express this with complex numbers, I can just use the result from the current. So it's R times I, and we have an expression for I already. So I could just write it R times I. More interesting is the voltage drop at the inductor. Here we have this phase shift of P half or 90 degrees in it. And therefore we can express it like this. Omega L stays the same. Then we take the amplitude of the current and divide it by the square root of 2. And then we use Euler's identity to express this phase shift of 90 degrees. So we just multiply this with J times P half. And what is this? Euler's identity when we have a phase angle of 90 degrees. It's on the imaginary axis, so this would be just be J. So we can write it like this. Okay, and now let's have a look at the capacitor. This here would be the voltage drop in time domain, and if I express it with complex numbers, it looks like this. This time we have a phase shift of minus 90 degrees in our function, and therefore I have here this Euler's identity with e in the power of minus j p half. And if we have a look in our complex plane, e in the power of minus 90 degrees is just minus j. And I could also express minus j by 1 divided by j. So that means we could write our equation like this. Okay, and here are the most important things on this slide. Let's have a look on the important things. So, we can use Ohm's law in our AC circuit, and it looks like this. At the resistors, it's no surprise, it looks just like Ohm's law as we always used it. At our inductor, it looks like this. And at our capacitor, it looks like this. Okay, and these expression j omega L and 1 divided by j omega C are the complex resistor values. They have a special name. We call them impedances. And if you have inductors or capacitors in an AC circuit, you can just deal with them as you know it from resistors in DC circuits. The only difference is that they have funny resistor values. So the resistance of an inductor is just j omega L, and the resistance of a capacitor is 1 divided by j omega C. But that is all. That's the only difference between AC circuits and DC circuits. And we call these complex resistances impedances. For resistors, we know the inverse value, and we call that conductance. And here we call the inverse value of the impedances admittances. And we use the letter Y for the admittances and Z for the impedances. And that's all. Now you know how to deal with AC circuits. Okay, let's train this a bit. Let's start with this complex description of voltages and currents. So let's say we have this voltage here in time domain, and the blue curve just shows how a sine wave with the amplitude of 1 would look like. So we have a phase shift compared to our sine wave, and we have an amplitude. And we want to express this voltage in the first step as a time function, and therefore, if we have a look here, our function has its 0 point here at 30 degrees, and it has an amplitude of 4.24 volts. And that means we can express our time function like this. And now we wonder, hey, why is there minus 30 degree? This is sometimes a bit confusing in the beginning, but if you think you want your sine function, your pure sine function is 0 when the argument is 0. And therefore you need a function where you put in for omega t plus 30 degrees, and there the argument has to be 0 to have the sinus become 0. And therefore you need this minus 30 degree in the argument. Okay, and if we want to express this with complex numbers, so it should look like this. And therefore we take the amplitude of our voltage and divide it by the square root of 2. This is just to get the RMS value of our sine wave. And then we have this phase angle minus 30 degree, and therefore we can express our complex number like this. And maybe you wonder why I've chosen such an ugly amplitude value. That was just because if I divide this voltage by the square root of 2, the result is 3 volt. And now we can draw the complex number in our complex plane, and it looks like this. The absolute value is 3 volt and the phase angle is minus 30 degrees. Let's do the same thing but the other way around. Let's say we have this complex voltage given. The absolute value is 1 volt and the phase angle here is 135 degrees. So we could write this complex voltage like this, and with our number values it's 1 volt times e in the power of j 135 degree. And that means that our time function looks like this. For our amplitude we have to multiply the absolute value of our complex number with the square root of 2. And then we have the sine function of omega t plus 135 degree. And if we want to draw this, it looks like this. Again, in blue is a usual sine function with a phase shift of 0 degrees. And I add the x and y axis here to give you a better overview. And here you see our amplitude and you see here our phase shift. And again, if we have a positive phase shift, that means that our time function moves to left. Okay, and now let's come back to our example from the beginning. And you now know that we can express all the voltages and currents as complex numbers. And the cool thing now is that we can just use our rules from Kirchhoff's voltage law and Kirchhoff's current law with these complex numbers. And I will show you how it looks like. Our current here was this sine wave, and we said this current has the phase angle 0. And therefore we could draw our current here in our complex plane. It's just a real number because the phase shift is 0. And then we had our voltage drop at the resistor. And at a resistor we have no phase shift between voltage and current, and therefore the voltage drop at the resistor is a real number in this example too. And now the voltage drop at the inductor has this phase shift of, what is a phase shift? Okay, let's think about the multiplication of complex numbers again. So we have our current, and this current is multiplied with a complex number j omega L. And j omega L is a pure imaginary number because we have this j in front of it. And now we multiply them. This means we multiply the absolute values, so omega L times the absolute value of I, and now we add the phase angles. Our current has a phase angle 0 degree, but J is phase angle of 90 degree. And if we add these phase angles, it leads us to plus 90 degree. So again, even here in complex numbers, you see that the voltage at an inductor is leading to the current of it. And now the voltage drop at the capacitor. Again, we multiply complex numbers with each other, and here we have this 1 divided by j. And if we divide by j, that means that we have to subtract the angles. And that means that this voltage is lagging by 90 degrees to the current. Okay, and now we've seen when we calculated with time functions that it was super hard to find the total voltage drop here. But now with our complex numbers it's super easy, because we can just add our complex numbers, and if we do this in our complex plane, this just means that we have, let's start here with UL and let's add UR, and now let's add UC, and we are finished. We found the total voltage drop at our load. So you see, dealing in a graphical way just in the complex plane looks super easy, and it is, and we call this diagram here the Phasor diagram, because we also call these complex numbers we use to express voltages or currents phasors. In the end, I want to show you an example how you can calculate an AC circuit with these complex numbers. So we have an ideal voltage source here, and it gives a sinusoidal voltage. You can see that this is a sinusoidal voltage source because the voltage I defined there is a complex number. You see it with this underlining. And let's say we know from our circuit the absolute value of the voltage, so it's RMS value. We know the angular frequency of our voltage, and we know the values L and R. And now we want to calculate the voltage drop at the resistor. Okay, if this was a DC circuit and if we had two resistors, we would know how to do it. You remember, you can just use the voltage divider rule. But now we have an AC circuit and we have an inductor in it. But everything we need is now the impedance of the inductor, which is J omega L. And with that we can use our voltage divider rule. So the voltage drop at the resistor is the total voltage from our source multiplied with the resistor value divided by the sum of the two impedances, and this is R plus J omega L. That's all, and it's that easy.